In this lecture, I am going to discuss the velocity analysis of planar robot manipulators, open chain. So, we are going to look at the velocity analysis problem for robotic manipulators. I am going to look at two examples, RR and RP open chain manipulators, and I will also introduce the concept of the Jacobian for velocity transformation. Now, as we have discussed before, the forward velocity analysis problem is about finding out the velocity of the output link. In the case of robotic manipulators, this is the end effector. So, the velocity vector at the end effector, the orientation rate of the end effector in terms of the input velocity, which are the actuator rates. In the case of rotary motor, it will be the angular velocity. In the case of linear motors, it is going to be the expansion rate. The inverse velocity problem is about finding out the expansion rates or the actuator angular velocity rates. So, given for a given output velocity at the end effector. Now, this velocity problem for robots is intimately connected to the motion planning or path planning of the robot. Now, here let us say this excavator, it has to follow this path. So, at each point of the path, the velocity vector is going to be tangent to the path. Now, as the bin moves on this path, its velocity is decided by this tangent vector. Now, given this position of the bin and given this tangent vector, what should be the actuator expansion rates, so that this velocity is achieved at this point, this velocity is achieved at this point. So, as the bin moves in successive positions, how should you change the actuator expansion rates? So, this comes from the inverse velocity analysis problem. So, this is the path generation problem. The forward problem, of course, is easier, in which we are given the actuator expansion rate and we have to find out the path. So, essentially at every point we know the velocity vector. Given the actuator rates, we know the velocity vector. If I know the velocity vector at a particular point, we know how the bin or the tip is going to move, and as I integrate that, we are going to get the path of motion of the tip. So, this velocity analysis problem for robots is important from motion planning or path planning point of view as well. So, our plan for velocity analysis is as follows. We are going to first discuss open chain robots. Subsequently, we are going to discuss closed chain robots, robotic manipulators. In this lecture, I am going to discuss two kinds of chains. One is 2R, the other is RP. So, this is a 2R planar manipulator. We are given the configuration. So, configuration needs to be given. This comes from the displacement analysis. We have to find out a relation between the joint rates, the joint angular rates, and the end effector velocity vector. So, the velocity of the point, this point of the end effector, so which is specified by this vector x e dot y e dot. We start with the forward kinematic relations which we have discussed before. So, the end effector positional coordinates which are given in the coordinates shown as x e and y e, and we had related this end effector coordinate in terms of the angles theta 1 and theta 2. Now, if you look at this angle phi, which is the orientation of the end effector, and that can be written as theta 1 plus theta 2. Now, starting with these forward kinematic relations, if you differentiate with respect to time, then you relate the rates at which x e is changing with the rates at which theta 1 and theta 2 will change. Similarly, for y e, therefore, we can assemble this and write it as a product of matrices. So, this is the end effector velocity vector, and we have this matrix 2 cross 2 matrix whose elements can be read out from these relations, and that gets multiplied by the joint rate vector. The orientation rate of the end effector is therefore related in terms of theta 1 dot and theta 2 dot, that comes by directly differentiating the orientation angle with respect to time. Now, this matrix J that relates the end effector velocity vector with the vector of the joint velocities is known as the Jacobian matrix. Now, Jacobian matrix therefore transforms the joint velocities to the end effector velocities. So, there is a relation, this provides a relation between the joint velocities and the end effector velocities. Therefore, given the joint velocities at a particular configuration of the manipulator, I can find out the end effector velocity vector, and if I move these joints, so subsequent velocity vectors and the joint angles will be known to me. So, joint as I move, given the joint angular rates, I can integrate very easily to find out the joint angles as it evolves with time, and given the end effector velocity vector, I can integrate to find out the displacement of the end effector, and that is how we are going to determine the path. Now, given so that is the forward problem. Now, given the end effector velocities, how to find out the joint velocities? This is just by inverting the Jacobian matrix, but something has to be borne in mind. In order to invert the Jacobian matrix, which relates, so the inverse of the Jacobian matrix relates the end effector velocity vector with the joint velocity vector, but in order to invert that, the matrix must be invertible, which means the determinant of this matrix which sits in the denominator in this expression must be non-zero. Only then we can invert. This is the adjoint of the Jacobian matrix. So, the determinant of the Jacobian matrix must be non-zero in order for us to be able to invert it and relate the end effector velocities with the joint velocities. Now, this non-singularity of the Jacobian matrix or singularity of the Jacobian matrix has certain implications which we are going to discuss in subsequent lectures. Next, we are going to look at the RP manipulator. In this manipulator, we have this angle as our variable and the throw of this prismatic actuator as the other variable. The angle alpha is fixed. Note that angle alpha is being measured in the clockwise sense, therefore, it is to be treated as a negative angle. So, the end effector position coordinates xc and ye are related by these expressions which we have already discussed. Here, as I mentioned, this angle, we in order to find out xc and ye. So, let us say the expression of xc, it is L1 cosine theta plus s, which is this length, cosine of theta minus alpha, this being the clockwise sense, the alpha. So, therefore, it is theta minus alpha. Now, if you differentiate this with respect to time, this is the end effector orientational coordinate. So, here also you find that phi is theta minus alpha. So, that is the orientational coordinate. If you differentiate these expressions with respect to time, you are going to get the velocity relations with the joint rates. Here I have differentiated these expressions. This involves the joint angle rate and the expansion rate of the prismatic actuator, and this can again be assembled in terms of this Jacobian matrix whose elements can be read out from the above expressions. Here the orientation rate of the end effector is just the joint rate of the manipulator. This is because the angle alpha is a constant. Therefore, we can write out the Jacobian matrix, and if you want to find out, if you want to relate the end effector velocity with the joint rates, you require the Jacobian, and if you want to relate the joint rates in terms of the end effector velocities, then you need to invert this Jacobian, and once again the same consideration comes up, the Jacobian must be invertible, or in other words its determinant must be non-zero. So, if the determinant is 0, then we cannot invert, which means we are losing some degrees of freedom, and this is what we are going to discuss in a subsequent lecture. So, let me summarize. We have discussed the velocity analysis of robot manipulators. I have discussed about how the velocity analysis problem of robotic manipulators is intimately connected to the motion planning or the path planning of the manipulator, which we are going to again look at separately in a future lecture. I have looked at the examples of RR and RP manipulators, open chain planar manipulators, and discussed the concept of Jacobian and how it relates the joint velocities with the end effector velocities, and the inverse of the Jacobian which relates the end effector velocities and the joint velocities, and the inversion of the Jacobian is key to determining the joint rates in terms of the end effector rates. The consequences of a non-invertible Jacobian, or where the or under what conditions the Jacobian becomes non-invertible. This we are going to discuss in a future lecture. So, with that I will close this lecture.